In this video and the next video, I want to discuss two new types of integrals of vector fields. In this video, I want to talk about the line integral of a vector field. The most common application is to compute the work done by a force on some mass. You usually have to compute the line integral of the force along the motion of that mass. How do we write this formally? The line integral is written as an integral over some curve of a vector field dotted into dr. Or another way you might see this, if the curve is a closed curve, meaning that the starting point of the curve is the same as the ending point, like a circle, say, then you would put a circle on the integral sign, and that would represent the integral of u dot dr around a closed curve. What does this mean computationally? So remember that an integral is a sum of infinitesimal amounts. This is called a Riemann sum. In this case of a line integral, the sum will be the little vectors making up the line, the curve, and then the vector field u dotted into those little vectors making up the curve. And then you sum all of them. Okay, so that's how you would compute this using a computer. But here in this course, we're interested in how do you do these things analytically when you can. So the typical way then to compute this integral is to parameterize the curve that you're integrating over. So we let r be parameterized by a parameter t. So sometimes t is time, but sometimes it can be something else. And then dr will become the derivative of the vector t, r, dr dt, times dt. Okay? So that the integral using this parameterization would be written as the integral of u at r, so at r, which is a function of time, dotted into dr dt, the derivative of the position vector with respect to time, times dt. And the curve then has some starting value and some ending value. So let's say r of t naught is the start of the curve. So we would put t naught here, and then r of tf is the ending position of the curve. So we would put tf here. Okay? That's how you do it by parameterizing the curve. So let's now look at a specific problem to compute. So you see an example of computing a line integral. Okay, so let's compute the line integral of the position vector r, xi plus yj in the xy plane from the point 0, 0, which is the origin, to the point 1, 1, x equals 1, y equals 1. So in this problem, I haven't specified the path. It turns out that the solution is path independent. We'll talk about that in later videos. But for now, let's then compute this using two different paths. So let me show you what two possible paths are. So this is x and y. So one possible path would be to go along the x-axis and then go along the y-axis. So we're getting to the point 1, 1. So here is 1, 1. So this is 1. This is 1. along this path. So the path has a direction, so we go along the x-axis, and then we go vertically along the direction of the y-axis. So let me call this path C1, okay? Composed of two line segments. We can choose a different path, so let's do the direct path. So x and y, so our point is here. So let's just go directly to that point, so we can go from the origin to that point along this path. Let's call that path C2, okay? So I want to compute the line integral along C1 and C2. So let's start C1. So what we are computing is the integral, right, along C1 of our vector field, which is R. So R here, dotted against dr. Okay? In this case, so typically you have to parameterize the curve. In this case, the first curve is just along the x direction, and the second curve is just along the y direction. So our dr in the first place is just along x, right? But along this piece here, so our dr is in the direction of x, so it's I, and then it will be dx. It's just a simple integral along the x direction. This path here, our dr is in the direction of j, and then has an element dy. Okay, so our drs are very simple here. This one is in the direction of x, so the vector is I, and then we're taking elements dx. The second line segment here is in the direction of y, so the vector is j, and we're taking elements dy. So this integral then is xi plus yj, right? I can write that out. It's the integral of xi plus yj, right? Dotted into the first path would be I dx, right? And here x will go from 0 to 1, plus the second line segment here would be r xi plus yj. And now we're dotted into j dy, okay? And y then goes from 0 to 1 also. So this is two integrals. The dotted into I just gives us x. The dotted into j just gives us y. So it's the integral from 0 to 1 x dx plus the integral from 0 to 1 y dy. The integral of x is x squared divided by 2. The integral from 0 to 1 of x dx then will be 1/2. The integral from 0 to 1 y dy is exactly the same. Here y is a dummy variable. Here x is a dummy variable. So that's 1/2 plus 1/2. So we get 1. I think everybody can do these simple integrals. Okay, so that takes care of this first path. Let's look at the second path now. So we want the integral along C2 of r dot dr. Okay? So here we have to parameterize r. So as we move along this curve, we have a position vector r, because this is the point 1, 1, right? This is 1, this is 1. So you have the x component is always equal to the y component along this path. And the vector direction then will be I plus j here. Okay? So this curve here can be parameterized as r. So the vector direction is I plus j, right? But we're moving from the origin to 1, 1, so that we can parameterize this by multiplying by a scalar t, a parameter t. So your position along this curve is given by the parameter t times the vectors I plus j, the unit vectors I plus j. Okay? And dr then is quite simple. Dr would just be dt times I plus j. Right? So this integral here is the integral along the curve. So it's the integral. In the parameter now, the parameter t is going to go from 0 to 1 of r dot dr. So let me write that out. R t of I plus j dot dr, which is I plus j, times dt. And to go from r equals 0, t is equal to 0, out to a vector pointing all the way to 1, 1, that would be the vector I plus j, right? I, the unit vector in the x direction, plus j, the unit vector in the y direction. And that occurs at t equals 1. So the parameter t then goes from 0 to 1. Okay, this dot product is simple. I dot I is 1, j dot j is 1, and I dot j is 0. So we pick up a factor of 2 here. So we have the integral from 0 to 1 of 2 times t dt. And the integral of t is t squared divided by 2. The division by 2 cancels the 2, so we get t squared evaluated between 0 and 1, which will just be 1 again. Okay, so let me summarize. I'm showing you now a new type of integral. It's called a line integral. It's an integral of a vector field, so we have to dot the vector field against the line element, u dot dr. The general method of doing this type of integral is to parameterize the curve that you're integrating over by r vector equals r vector of t. T is the parameter. Then this dr becomes dr dt dt. And then we're dotting u into dr dt and integrating over dt. The limits of the integral corresponds to the beginning point of the curve and the ending point of the curve in the parameterization. So I gave you 2 examples of a line integral. We're integrating the same function, but I'm choosing 2 different curves. So we end up with 2 integrations here that are different. But it turns out that the solution of this particular line integral is independent of the path. It just depends on the starting point and the ending point. So the integral over C1 turns out to be equal to the integral over C2. We'll have a little bit better understanding why that sometimes occurs in some later videos. I'm Jeff Chasnoff. Thanks for watching, and I'll see you in the next video.